All right, so we're going to talk about hybridization of atomic orbitals. And just like you would think of when something's hybridized that you're familiar with, let's say hybrid cars or hybrid brakes, there are two ideas of two separate types of cars, one being electric and one being gas, and kind of combining together to make a new hybrid car. It's a completely new, different type of car. Or bikes, for example, mountain bike and road bike, they come together to form a new type of bike called a hybrid bike. We're going to do the same thing with atomic orbitals. We're going to bring two different orbitals together to make a completely new orbital. We're going to call that process hybridization. A process in which atomic orbitals are mixed to form new identical orbitals. So these are identical in energy. All right, so let's talk about why we're actually going to do this. Why is this even necessary? So let's start with an example of carbon tetrachloride. All right, so carbon tetrachloride is a single carbon atom bonded to 4 chlorine atoms. So we have to agree that all of these bonds, these 4 bonds, are equal in energy. One is not more energetic than the other. One's not more special or anything than the other one. So how do we make sure that that's the case? When you look at the orbitals that carbon has in the valence shell, we have a 2s orbital and we have 3 equal in energy p orbitals. Okay, so we know carbon has 4 electrons. We're going to denote them. Okay, so we want to have 4 equal places where chlorine can come in and bond with this carbon. So we're going to hybridize all these orbitals to make 4 equal in energy orbitals. So we're going to have 4 new orbitals, and we're going to call them the 1s, and 3 of them are from p, so we're going to call it sp3. 1 from s, 3 from p. And we're going to spread these out just like Hund's rule tells us to, and we're going to say, okay, we have 4 electrons, which gives us 4 equal places for chlorine to come in and actually bond with that carbon. So chlorine can come in here, 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 and here, and make 4 of those bonds, like you see in the picture. All right, so what actually will get hybridized? What do we create that actually makes it so that these equal orbitals are necessary? So we know all single bonds are going to be hybridized because single bonds, there's not one that's more energetic than the other. So all single bonds are going to be hybridized. Because they're hybridized bonds, we're going to now call single bonds sigma bonds. It's just the way they overlap, the way the orbitals overlap. We're going to denote them sigma bonds. And we also want to say that lone pairs are also going to be hybridized because they're not higher or lower in energy than those bonds either. So let's look at ammonia as an example. Ammonia, if you look at nitrogen within ammonia, it has these 2 lone pair of electrons. So ammonia before had the same thing. Ammonia has 5 valence electrons, so 2, 3, 4, 5. These should be the same. I'm sorry, they're kind of uneven. They should actually be the same in energy. And we have the 5 electrons. We're going to hybridize all of them. We need to have 1, 2, 3 of these are the same along with this 4th one. So we need to have all 4 of these the same. So we're going to have, again, 4 equal in energy. We're going to call it sp3, 1 from s, 3 from p, 1, 2, 3, 4, 5. Here's our lone pair, and here's the hydrogens are going to come in and bond with them. All equal in energy. So we have these new hybrid orbitals. Okay. What about when we have multiple bonds? There are definitely cases when we have multiple bonds, double bonds and triple bonds. So what happens in those guys? Well, one of those bonds within a multiple bond is called a sigma bond. And again, don't forget, sigma bonds are hybridized. So one of those bonds is going to be hybridized. The rest of those bonds are called pi bonds. Those pi bonds are just p orbitals overlapping each other. They are only p orbitals. They're a little bit higher in energy. They actually are different in energy. So we're going to actually keep them separated. So we have 1 sigma and 1 pi. So let's look at carbon dioxide here. We have a double bond. All right, one of these is going to be a sigma bond. And we're going to denote that with a sigma. And one of the bonds is going to be a pi bond. We'll denote that with a pi. These are only p orbitals. These are hybridized orbitals. We're just talking about the carbon right now. Okay, so carbon we already know looks like this. But we want to save 2 of the p orbitals, and I don't care which 2 I save. It doesn't really matter. They're all the same in energy. I don't care. I'm just going to save these just for practical purposes. These are going to be the ones used in pi bonding. So I'm going to save those so I can hybridize 1s and the other p. So instead of being sp3 this time, it's just going to be sp, 1s and 1p. sp orbitals. Let's look at the oxygen. Oxygen it also has a sigma bond, a pi bond, but notice it has the lone pairs. So the sigma bond and the lone pairs are going to be hybridized, but not the pi bond. We're going to leave this alone. So we need 3 hybrid orbitals. 1 from p and 2 from, 1 from s and 2 from p. So it's going to be sp2. So this guy is going to be sp2. This guy was sp, don't forget. hybridized orbitals, or sp. It doesn't matter that these guys have different types of orbitals. We just want to make sure that the orbitals within the atom itself are the same. So let's look at triple bond. Triple bond, one is sigma, don't forget. So we're going to say this is sigma. And these two are pi. Okay? So these two are just p. We're going to ignore them. And this nitrogen needs two, one for the lone pair and one for the sigma, hybridized orbitals. So we need two, one from s, one from p. So we're going to call this sp. This also is just sp. If we look at ozone, O3, all three of these are a little bit different. So this guy has 1, 2, 3 lone pairs and 1 sigma bond, so it needs 4. 1 from S, 3 from P, so it's going to be sp3. Oxygen is going to need, it has 2 sigma bonds, 1 from here, and the lone pair, so it needs 3, so it's going to be sp2. 1 from S, 2 from P. This guy over here has 1 sigma bond and 2 lone pairs. Again, it's 3 hybridized orbitals, so it's going to be sp2, 1 from S, 2 from P. So hopefully that made it a little bit easier for you to figure out hybridized orbitals.